Today we're going to be talking about resting membrane potential. This is a topic that really confuses a lot of students, so we're going to be taking it one step at a time. So let's begin with that why question. Why do we have a resting membrane potential? Now, in order to understand this, we need to understand two very, very important principles. The first one is the principle of equimolality. Now, this purely states that the amount of osmotically active particles outside of the cell need to match the amount of osmotically active particles inside of the cell. As we know, both sodium and potassium have a +1 charge, meaning that they cannot freely diffuse across the cell membrane. However, they can strongly influence the degree of water flowing across the cell membrane. Now, if we did not have an equal concentration here, if we had a lot of solutes on the outside of the cell and very minimal solutes inside of the cell, water would actually be drawn out of the cell, causing that cell to dehydrate and eventually die. Now, in our bodies, this can lead to coma and death. So it is very important that we have an equal distribution of osmotically active particles inside and outside of our membrane to establish that homeostasis. So the second principle is of electrical neutrality. Now, this purely states that the amount of cations outside of the cell need to match the amount of anions outside of the cell. Now, this is important because in our physical universe, things like to be neutral. They like to go from a high energy state to a lower energy state, reaching that stability. That is just a fundamental principle of our natural universe. So these two principles are very, very important when we're trying to understand resting membrane potential. Now let's talk about how we actually achieve our resting membrane potential. And to do that, we need to talk about potassium. So our membrane is actually more permeable to potassium due to the presence of more potassium channels. These are actually called leak channels, and they open and close at random. Now, because we have lots of potassium inside of the cell, the chemical gradient when these leak channels open is to push potassium outside of the cell because we have more of potassium inside of the cell. So if we were to open potassium channels, potassium would tend to leave the cell because we have a high concentration, and as one of our laws of our physical universe, things like to go from high concentration to a low concentration. So as potassium leaves the cell via these leak channels, they actually leave behind unmatched negatively charged ions. Now, in the intracellular fluid and extracellular fluid, we do have electrical neutrality. However, because potassium is leaving the cell, we end up having this cluster of positively charged ions around the cell and the clustering of negatively charged ions in the cell membrane. Now, because of this clustering of charges around the cell membrane, we end up with a slightly negative membrane potential, and that is that magic number, -70 millivolts. Now, this is really important for us to understand, but it all comes back down to the cell membrane being more permeable to potassium. I want you to go through this video a few times and make sense of it, but this is the fundamental nature of the resting membrane potential. Now, in our next video, we're going to be talking about the sodium-potassium exchange pump and why it is important in maintaining that resting membrane potential. Thank you very much, guys. I hope you enjoyed the video, and I'll talk to you all soon.